In the previous module, we read in some data, some reduced representation bisulfite sequencing data for 2 mouse oocytes and 2 mouse zygotes. We did some basic QC on the data, and we converted it into a BSSeq object, which is called QC'd data. In this module, we're going to use a few different approaches to analyze this data. The first one is going to be what I think of as a little bit of a naive approach. The Fisher exact tests, they're nice when all of the assumptions underlying the Fisher's exact test have been met. But in this case, what we would be doing is we would be collapsing the 2 oocytes together, considering them as one data point, and then collapsing the 2 zygotes together. And that, to me, violates the assumptions of Fisher's exact test. The reads should all be independent, and when you have 2 or more samples that have biological variation between them, the reads are no longer independent of each other. So Fisher's exact test isn't the greatest way to analyze this data, but it is a common way. And they make it available in the BSSeq package in case you want to do it. So the first thing we'll do is we'll run Fisher tests to perform Fisher's exact test on each of the we had 15,000 CPG sites that we QC down to a little over 12,000. So for each of the 12,045 CPG sites, this will run a Fisher's exact test. It actually happens pretty quickly. They use a very efficient method to do this, and I'll show you. We can, by inspecting the object, the resulting object which we've named Fisher test, you can see exactly how they did it. So here we can use the names command to see what's available, what objects are available in Fisher test. And so there's 2. There's results and lookup. And the results are probably what you think they are. So we can use the head function to look at the results. And so the 2 elements we get here are the p-value and the log to odds ratio. And we'll use a Manhattan plot to plot the p-values in a minute so we can see how significant they are. But I want to look at the other object first. The other object is called lookup, and it's not obvious what that is. And if you look at it, it might not at first be obvious what this is. It seems to have the same data in it as the results object. However, if we take the dimension of each one, they're going to be a little bit different. So we take the dimension of results, and we've got all 12,045 CPG sites. We have 1 row for each of them. And then if we do it again for lookup, here we only have, we have under 12,000 data points, under 12,000 rows. And at first, it's not clear why, but if you look at these, each row has a row name, and the row names seem to be 4 numbers. And actually what these numbers are is if you know that if you do a Fisher's test, you make a 2x2 table. These are the elements of the 2x2 table. So in order to be efficient for really, really large data sets, they have taken CPG sites which would have the exact same elements in their table and just collapsed them so they only have to do each Fisher test once. And this saves just a little bit of time. It probably doesn't make a difference with a small data set like this, but if you had the whole genome bisulfite sequencing data for every chromosome, this could make more of a difference. And so we ran the Fisher test. Now we can make a plot of the results. We'll make a Manhattan plot just to see what the p-values look like. And you might remember from Module 1 that we have data just from chromosome 18. It's reduced representation data, which is why we only have 12,000 sites that we're analyzing. So along the x-axis of this plot, we're going to ask it to put the position. And Z1 is one of the elements that we played with in Module 1. And you'll recall that there was a column called pause for position. So we're going to plot the position along chromosome 18 on our x-axis. And then the y-axis is going to be the negative log base 10 of the Fisher test p-value. And you'll see why if you haven't seen this before, you'll see why we use the negative log 10 of the p-value. It displays it in a very nice way. And then here we just have some plotting options and labels. And then we're also going to draw a line across it. This is actually an overly conservative p-value cutoff. If we did a Bonferroni correction, we could actually get by with a larger p-value, but it's going to turn out not to matter because everything is just so significant. So let's just plot this and then we can talk about it. Okay, so here's our Manhattan plot. I can make it horizontal to make it look like a real Manhattan plot. It's for just one chromosome, chromosome 18. And so along here we have chromosome position along the chromosome, and then here we have the negative log p-value. And you'll see that there are some that are way up here. And because this is the negative log base 10 of the p-value, that means that the number 150 corresponds to 10 to the negative 150th. So this is a very small p-value up here, and we have a lot of equally small ones across the genome. These are kind of ridiculously small, and that's why I didn't think it didn't end up mattering too much where we drew the cutoff. You can see so much past the cutoff. And I'm a little suspicious of this Manhattan plot just because of what I said about how the Fisher test isn't a very appropriate test to do in this situation. So we're going to come back to this later after we've performed some more appropriate tests, and we'll compare this to what we get then. So that was the Fisher's exact test. We're next going to try a smoothing-based approach. And we'll start, I mentioned in Module 1 that you were going to get to smooth some data in Module 2. Here's where we do it. And so we're going to use the bsmooth function, and that's a part of the bsseq package. Before we do that, let's use the help menu just to see what bsmooth is all about. And I love R because it has such consistent help menus for every single function. They really tell you a lot about what you need to know. So the first part is usage, and that just gives you the basic syntax. And then it'll define all of the arguments. So from there you can see what bsmooth wants is they want a bsseq object, which is good because we've already made one. It's called QC_data. When you see the arguments in the syntax and they have it's set equal to something, these are the defaults. So they've already set defaults for most of these options. That means if we don't specify the option, they'll just use the defaults. The first two, the second argument and the third argument here, NS and H, pertain to the window size that we're going to use for smoothing. And so NS is the minimum number of CPG sites that would define a smoothing window, and then H is the minimum size a smoothing window should be in bases. And so they're saying the smoothing window should be no smaller than 1 KB and 70 CPG sites. Okay, so what we're going to do is run bsmooth. We're going to give it our QC_data object. This is our bsseq object that we're giving it. And we're going to leave the window size as the default. You might remember that H equals 1000 was the default anyway. So we're just going to go ahead and smooth these data. What we can do once we've smoothed the data, we can actually look at it if we want to. So here I'm just going to define, I'm picking an arbitrary region. We're just going to, we'll look at some more interesting regions later. But for our first look, we'll just do this arbitrary region. I'll go ahead and plot it. And that looks really smooth. We actually can't see the points here, so it's actually better if we use a different option. When we plot the region, there's an option called add points equals true. And if you want to see all the different options for plot region, you can peruse the help menus. Okay, so there, now we've added the points. And so this is, I really like this format. It shows you a gray line everywhere where there's a methylation site. And then all the points along, and some of them are actually dense gray lines on top of each other, which is why there's more than 4 points in a lot of places. And recall that this is RRBS data, so it is going to be a little bit kind of chunky, like there are CPGs here, there are CPGs here, but then there are these big white spaces we didn't include. There are just kind of holes in the genome. And so you end up with a lot of CPG sites in these CPG-rich regions, which is why you see more than 4 points per line. You see a lot of them clustered. The methylation proportion for each sample is plotted along this, and then the smooth curve has been fit to it. And you might notice that with the RBS data, it can be a little bit hard to fit a smooth curve to it because of the chunky nature of it, and because it's very sparse in between CPG-rich regions. And so the curve looks like it fits the points a little. Maybe we should have tried a different smoothing window that's not clear. We could try it with a different smoothing window. We'll do that in a sec. We can also run a Ttest. So we do have 4 lines, one for each of the samples. We had the 2 oocyte samples and the 2 zygote samples. And just so we can look back at our command, we've asked it so our 2 oocytes correspond to, the first 2 have color number 2. And in R, color number 2 corresponds to red, and then the zygotes have color number 4, which corresponds to blue. So we have 2 red lines for the 2 oocytes and 2 blue lines for the 2 zygotes. And this is just a small portion of chromosome 18. We have the coordinates written up here. But we do have data across all of chromosome 18. So what we could do is for each point along chromosome 18, we could perform a little Ttest within bsmooth to check whether the smooth lines are significantly different for the oocytes versus the zygotes. And this is a way we could identify differentially methylated regions. And so we can try that. So bsmooth tstat is another function. We could check out their help menu. And again, it's going to want to be a seq object. It wants us to tell us what the 2 groups are. We have group 1, we have group 2. We get to choose how they estimate the variance. We can give it same paired or group 2. And then there's some other options as well that we won't worry about. Okay, so here we're going to run the bsmooth Ttest. We're giving it the oocytes versus the zygotes as the 2 groups. We've asked it to estimate the variance using both groups this time. That'll change in our next example. Okay, so it's run a Ttest. We can inspect the t-statistics that come out of the Ttest. I've used the get_stats function to get the test statistics out of the smooth data tstat object that we created. We can use head to inspect the t-statistics for a few of the CPG sites. And so it's giving us a lot of information. It gives us the means for each of the 2 groups. This is the standard deviation that is used to compute the T-stat. This is the T-stat itself. And they also have a corrected version of the T-stat. And that's interesting. We're going to talk about that in the next module. We won't worry too much about it for now. When we find the differentially methylated regions, the default is to use the corrected T-stat, but we'll talk about this more in module 3. If we want to compare the two T statistics, we will notice that one is more variable than the other. We can run these two lines to see the variance. We can run these two lines to see the variance. And it looks like the corrected one, which is in column 6, has very low variance, and the uncorrected one has very high variance. And this will be different depending on things such as smoothing window. We're next going to try it using a different smoothing window, and then we'll kind of compare our results. Now we're running the bsmooth command on our QC data again, but now we're going to make the window size, the number of CPG sites that have to be in a window is really small, and that's because we have such sparse data. It seemed like this might be another thing to try. So we'll try it with this smaller window. And we can then go ahead and plot the region again. And I'll do line 113 where we add points to the plot. Okay, so now the plot looks a lot jumpier than it did before. It does look like the curves that were fit for each of the 4 samples fit the data a lot better than before. But you wouldn't call these smooth anymore. They're very jumpy, which is kind of how our BS data are. So maybe this is a more appropriate way to smooth it to the data. It's not really clear. If we can then compute a T-test using the data smooth with the much smaller windows. Okay, on line 115, we ran the T-test on the smoothed data. On line 118, we will grab the stats from it, and we can inspect it on line 119. And this looks similar to what we saw before. Now, we still have these 2 different kinds of T-statistics, 2 different flavors. Because we took the variance of them before, I'm going to take the variance of them again, just so we can compare. I'll do it by column number. We have the 5th column and then the 6th column. And you might remember from earlier, the variance of the 5th column in the data smoothed with the wider window, it was a variance of 1 for the regular T-stat and a variance of near 0 for the corrected. Now it's different. Now the variance has gotten lower for the uncorrected and higher for the corrected. And we'll talk more about what those 2 statistics are in module 3. So we've now computed T-statistics using 2 very different window sizes. If we want to compare them, we could plot them. Okay, so we're going to plot it for the uncorrected T-statistic first. And it's interesting because this is the same data. All we've done is use 2 different window sizes, but you don't see a large amount of correlation between the statistics computed using the 2 different window sizes. You do see some points up here where they seem to have had high T-statistics in both scenarios. And we can do this again for the corrected T-statistics on line 123. And now we get kind of a crazy plot. And that's, you might remember the corrected T-statistic was close to invariant for the wider window, but then when we had the narrower window, it had some variability. And that has to do with the function of these statistics. So the corrected T-statistic turns out it's optimized to find smaller regions. So it probably does work better when you have the smaller window size. Okay, so now we'll use the DMR Finder function to identify which regions might be DMRs. And I'm going to do it for the second group of T-statistics that were obtained using the smaller smoothing window, because when I tried it for the first one, we found absolutely nothing that was significant. And DMR Finder does use the corrected T-statistic, so that's probably why it was almost invariant for the first one. So for the smaller window sizes, we can go ahead and run DMR Finder. We'll create an object called OZ-DMRs for oocyte zygote DMRs, and then we'll inspect it. So with this cutoff, T-statistics that are less than -4 or greater than 4 should be what goes into is the cutoff for defining a DMR. And this is actually a pretty liberal cutoff. It doesn't adjust for very many multiple tests, and even then we did not find any using this cutoff. So we're going to go even more liberal and try it with T-statistics where the absolute value exceeds 3. And so we could try this and inspect our data object, OZ-DMRs, our results object. So here we actually did get some DMRs. If we look at the dimension of OZ-DMRs, it'll tell us how many we got. And so it looks like we got 8 DMRs. That's actually all of them. I printed all of them there. It gives us a lot of information about each DMR. Some are hypermethylated versus hypomethylated, and you can see this if you compare the two means. Like in the hypermethylated one, the oocytes have more methylation than the zygotes. They're close to 70%, and the zygotes have around 26%. And then here's a hypomethylated one where it's hypomethylated in oocytes relative to zygotes. So it's unmethylated versus hemimethylated. And so you can see the two means. You can see the standard deviation that was used to create the t-statistic. They don't print the t-statistics here, but we know they're all greater than 3 in absolute value. Oh, actually, here's the t-statistics. And so these are, it's called max stat. And you can see what the mean difference are. These are some pretty large mean differences. And so because we have so few samples, it takes a pretty large mean difference to get us a significant t-statistic. You can also see the region size. You can see the start and end of the regions, and from there you can get the region sizes. The width column here tells you the width of each region in bases, and you can see these are actually some very small regions, which does make sense. We based this on a very small smoothing window, and the corrected t-statistic is optimized to find smaller regions, but we didn't find anything when we looked at the larger smoothing window either. This may have something. There may be a limitation with attempting to find differentially methylated regions in sparse data, such as RRBS data. It may, because a few of these down here with just a region width of 1 appear to be differentially methylated loci rather than regions. And so here it may make more sense to focus on finding differentially methylated loci. And so that's what we will do for the rest of Module 2. And then in Module 3, we'll come back with some much denser whole genome bisulfite sequencing data and attempt to find differentially methylated regions there. Okay, we can make plots of our 8 regions, though, before we move on to the differentially methylated loci. We'll define a range and then plot all of each of the 8 regions. Okay, and I've used part ask equals true, which means you have to keep hitting return, but then it's going to loop over and plot all of them. And so there's one. There's another. And you can really see the sparseness of the data here. They look like they might be differentially methylated right around here, but it's not very striking. It's hard to do this with RRBS data. And we can keep going. And you're welcome to go through and look at all of the regions yourself. I'm going to just kind of speed through them here so we can keep going with our tutorial. Another thing we can do is plot the t-statistics that we found using bsmooth to the Fisher test-based statistics. And so we'll make a plot of using the uncorrected t-statistics first. There it is. And so the first thing you'll see is there's very little correlation between the t-test and the Fisher test, which I find it concerning, but as I mentioned, the Fisher test probably wasn't the most appropriate way to handle these data. What you'll see is that the negative log 10 p-values for the t-statistics are very conservative, and none of these are going to be very significant, and they're crazy significant for the Fisher tests. And we can do that again. We did that for the uncorrected t-statistic. We can do it for the corrected as well. And we see about the same pattern here. We also see the lack of correlation. Okay, so moving on, we're going to try to identify differentially methylated loci instead, since with the RBS data that may be a better approach. So for this, we're going to use the DML test function from the DSS package. The DSS package also works with BSSeq objects, and so we can feed it our QC data object, as well as telling it which 2 groups we would like to compare. And you can read up more about DML test in its help menu. So we can run DML test and we're creating something called DML test result. And this part will take a little while, but not that long because this is a very small data set. And we can then, let's say we can inspect what we got. We got some results. Let's look at the dimension of results. And there's 12,000. So the majority of the CPG sites got in. A few were removed for other issues. Probably to do with additional QC. We can use head to examine the top of the file. Okay, and so you can see it gives us statistics that some of the statistics are similar to what we saw with bsmooth. We get sort of estimates of the means for the 2, although The mu1 and the mu2 are estimated in a very different way. They're the means estimated based on this Bayesian hierarchical model. And you can find out more about this by reading the paper that goes along with the DMR Finder in DSS. And so here we have the two means. We have the difference in the means. We have the Wald statistic, which results from it. We have estimates of the dispersion. We have a p-value, and then we have an FDR-corrected p-value as well. And this is for each position along chromosome 18. We can identify which of these loci are significant. We have 12,000 of them right now, but we can use the call DML function to determine which are significant. And you would think that we need to specify a cutoff for this. So let's use the help menu of call DML to look at that. So the call DML function takes as arguments the results file from the DML test that we just ran, and then two arguments which are used to assess significance. First, there's the delta, which is a threshold. It's a threshold in the difference between mu1 and mu2. So we want mean differences of 0.1 or greater by default, although we could change this. And then the default p-value threshold is 10 to the negative fifth. And we could change this as well, but for the purposes of this tutorial, we'll just leave it alone for now. Okay, so we'll run DML result just kind of using the default settings. And we'll let it call some differentially methylated loci for us. We can see how many it called. And it called 123 of them. So we can use the head function to look at just the top of the matrix. And so these are, the p-values are 0 because they're just so close to 0 that it's not going to actually print it all out for you. So these are some very significant differentially methylated loci. You can see that the differences between, we're talking about fully methylated in oocytes and unmethylated in zygotes, or vice versa, as in the second row. So these are some very significant loci that it's identified. We found 123 of them, which seems low compared to what the Fisher test found. So we can compare, just like we did with the Ttest, we can compare our results for the Fisher versus the p-values obtained via DSS for our differentially methylated loci. So we'll remake that Manhattan plot we made earlier for the Fisher test, and we'll make another one for this DSS-based analysis and just compare them. And you can see the results are pretty different. We don't have these wildly significant p-values down here in the DSS results. We do have some p-values that they pass our threshold for significance. With only 4 samples, you wouldn't really expect to see p-values on the order of 10 to the negative 150th. The way the Fisher test is able to get there is because in Fisher tests, the unit of observation is not samples, but it's reads. And so if you have high coverage for 4 samples, this could be about 200 reads. And so it's giving you an effective sample size of 200, which probably is a little bit of an artificial inflation of our sample size, to say the least, especially since the assumptions necessary for Fisher's exact test aren't really being met. The reads are not independent of each other. For oocytes, we have 2 different oocyte samples contributing reads, and so the reads within each oocyte would be correlated with the reads within that oocyte. And so you have 2 kind of distinct clusters going in, and they're not independent. So the Fisher test was not really the appropriate way to analyze these data. The B-Smooth or DSS were more appropriate. They account for all of the variation, including both the biological and the technical variation. And so when you run DSS, you do get this more conservative, more conservative set of results. We saw this with B-Smooth as well. We had more trouble detecting differentially methylated regions because of the sparseness of the data. So this is the end of Module 2. In Module 3, we're going to read in some already processed whole genome bisulfite sequencing data. So it will be much denser, and we'll be able to actually look at some interesting differentially methylated regions. So stay tuned for Module 3, and this is the end of Module 2.